Now in circles we also have something called inscribed polygon. And so we just talked about inscribed angles. Now inscribed polygon is pretty similar in the fact that it's also contained in the circle. However, it's a polygon whose vertices lie on a circle. So instead of one vertice, it is all the vertices of this polygon. So I see in this example here, this pentagon is an inscribed polygon because all of its vertices are on the circle. So that's called an inscribed polygon. And the circumscribed circle is a circle that contains the vertices. So this black circle here is that circumscribed circle. And so we have two different theorems that come from these inscribed polygons. The first one deals with right triangles. And we have two different parts here. And that says if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. And then on the flip side of that, if one side of an inscribed triangle is a diameter, so important here, diameter of the circle, then the triangle is a right triangle and the angle opposite the diameter is the right angle. And so what we see here, I have this circumscribed right triangle here. I know it's a right triangle because AC is the diameter, and I know it's the diameter because it's going through my center D. And so that would mean that angle B is a right angle, and I have a right triangle. And then we get to the inscribed quadrilateral theorem that tells us a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So I see here my opposite angles are first A and D, and so that would mean that angle A angle D is equal to 180. And I see that B and C are opposite angles, so this would mean that measure of angle B plus measure of angle C is equal to 180. Because remember, supplementary just means that the angles add up to be 180 degrees.